Okay, our last practice question. We see a graph in a shaded area, so at some point we would think we have to find the value of the shaded area. But let's read the question. So the diagram shows the points A and B, they give the coordinates, line on a curve with an equation, and we have the equation. All right, well, that's lovely, isn't it? The question then says, find the coordinates of the maximum point on the curve. The maximum point is right at the top of the curve, of course, and we know that as a stationary point, or in this case, it's also a turning point. And what we know about that point is the gradient is 0, and that's how we find it. We find the gradient, make it 0, and that will give us the x value, and then we'll find the y value of the point. Okay, so let's do it. We need to do the derivative. So dy dx is equal to, and the function is just right above us. So 9x becomes 9. We have a chain rule that we need to use now. And so the 3 on 2 is going to come out the front from the index. And also we're going to differentiate what's inside the brackets. And that will give us a 2. We leave the brackets the same, 2x plus 1. And we subtract 1 from the power and we get a half. And that is the derivative. Okay, so we're trying to find where the derivative is 0. So we will say that 9 minus, all right, so we get 2 cancels with 2, and we're just left with 3, 2x plus 1. Of course, to a power to a half means it's a square root, and that equals 0. All right, how are we going to solve this? We're going to take the negative whole thing to the other side and say it equals 9, and then divide both sides by 3. And we would end up with the square root of, I'm going to write it this way now, 2 plus 1 is equal to 3. Or you could just look at that and go, well, the brackets to the power of a half times 3 is 9, and 9 minus 9 is 0, which gets us there as well. Right, square both sides, and we'll get 2x plus 1 is equal to 9. Subtract 1, 2x is, well, let's do both things. Subtract 1, we get to 8, and then divide by 2, and we'll get x equals 4. All right, we want to find out the y value. This is the coordinate of the x coordinate of the maximum, because that's where the gradient is 0. To find the y value, we're going to put 4 back into the equation. And so we get 9 times 4 minus 2 times 4 plus 1 to the 3 on 2. Okay, so the 3 on 2 as index tells us do the square root and cube it. So hopefully that's not too hard to do. 9 times 4, 36, and we've got in the brackets 2 times 4 is 8, plus 1 is 9, so actually it isn't hard to do. So we're going to do the square root of 9 and then cube it. The square root of 9 is 3, and we cube 3, we get 27, and so we end up with y is 36 minus 27, which is 9. Okay, so the maximum point is the x value is 4 and the y value is 9. And we're done. Okay, moving on, we get to B. Verify that the line AB is the normal to the curve at A. All right, what do we know about the normal is the gradient of the normal times the gradient of the curve is equal to -1 because they're perpendicular to each other. All right, so we need to find 2 things. We need the gradient of the curve at A, and we need the gradient of the line AB. All right, let's do the gradient of the curve first. We know this, that dy dx that we found out is equal to 9. Let's write it slightly more simply. And the square root of 2x plus 1. All right, so at A, the x value is 1.5, which is 3 on 2. So x is 3 on 2, which tells me the gradient at A is going to be 9 minus 3 square root of 2 times 3 on 2 plus 1. It's nice how these questions work out really nicely. 2 times 3 on 2 is just 3. We're looking inside the root sign there. And 3 plus 1 is 4. And the square root of 4 is 2. And 2 times 3 is 6. So we end up with 9 minus 6. I don't know why we wrote that. We could have just written the gradient is 3. Okay, so now we want to find the gradient of the line AB. And to do that, we're going to use gradient between 2 points. So gradient between 2 points, y2 minus y1 over x2 minus x1. What are we expecting it to be? Well, the negative inverse of 3. So we expect it to be negative a third. What are our points? Oh, they're all fractions. So we're going to get 3.5. This is the by value. So let's turn 3.5 into 7 on 2. And we're going to subtract the other y value, 5.5. Oh, at least, oh, all the halves cancel. All right, this is good. That's 10, 11 on 2. And then we're dividing that by x. 7.5 is 15 on 2. And we're minusing 1.5, which is 3 on 2. All right. What have we got? We got 7 minus 11 is 4. And 4 divided by 2 is just 2. And we've got 15 minus 3 is 12, and 12 divided by 2 is 6. All right, and we should have actually made that negative 2 on top, because 7 minus 11 is negative 4. Negative 4 divided by 2, negative 2. All right, and I made that fix because I knew it should be negative, right? Negative a third, and it is negative a third. And therefore, AB is normal to the curve, because at the curve, the gradient is 3, and the gradient of AB is negative a third. All right, we probably should write something along those lines. AB is normal to the curve as 3 times negative a third is equal to negative 1. Done. Right, and part C, that's what we expected. Find the area of the shaded region. I think that's the last part, so let's go have a look at the function again. Okay, to find the area of the shaded region, we're going to find the area under the curve. We're going to integrate between 2 points, and that actually gives us that whole area under the curve. So we need to find the area under the curve and then subtract the area under the line. Normally I would do that as the function minus the other function, but in this case, it looks like it might just be easier to find the area of that shape. It's a trapezium, and it's fairly easy to find the area of a trapezium. So if we find the area under the curve and then subtract the area of the trapezium, it seems like that would be maybe a easier way to go, maybe a faster way to go. Let's just consider the area of the trapezium for a sec. What are the x values? 1.5 to 7.5. So that's 6. If you add 6 to 1.5, you get 7.5. And we've got 5.5, 5.5, and 3.5 for the 2 y bows. So they're parallel lines. All right, and you know, all right, so we already know the area of this trapezium. It's so easy. The area is the height on 2, a plus b. In this case, a and b are the parallel lines. So we get 5.5 plus 3.5. They're the 2 parallel lines, and the height is the distance between the parallel lines, so it's 6 on 2. That's why I told you it was easy. Because 6 divided by 2 is 3, and 5.5 plus 3.5 is 9. So we've got 3 times 9, which is 27. Okay, so the area under the straight line is 27. We're going to have to show that later. All we have to do really is find the area under the curve and then subtract 27. All right, that's our process. Let's get to it. Yeah, why I'm erasing that took so long. Why did it take so long? All right. Area under the curve. We are going to integrate from the first x value, 3 on 2, to the second one, 15 on 2, of the function, which is 9x minus 2x plus 1 to the 3 on 2 with respect to x. All right, that's our job. Let's work this out. I'm just going to go to the next line here. When we integrate 9x, well, the x came from x squared, and we have to divide by the 2, so we get 9 on 2. Let's put the square bracket out the front. We've now got a chain rule, and let's work on that. So the brackets would stay the same because of the chain rule, and the power, we're going to add 1. So 3 on 2 is going to become 5 on 2. All right, so we're working backwards now. That 5 on 2 would have come out the front, so we need to get rid of it by putting 2 on 5, which would cancel the 5 on 2 when we differentiate. And when we differentiate, it also puts a 2 out the front, and so we need to get rid of the 2 that comes out by multiplying by a half. And that's it. All right, so the minus sign can stay there, and we are done. So we're still going from 3 on 2 to 15 on 2. And yeah, the only difficulty that we have here are the fractions. Okay, so we put the 15 on a 2 in first, and we're going to get 9 on 2 times 15 on 2 squared minus, let's make that a little nicer, it's 1 on 5, and we're doing the square root raised to the power of 5, so let's just write that. The square root raised to the power of 5 of 15 on 2. So 15 on 2 times 2 is just 15, and 15 plus 1 is 16. I didn't need such a big one. And that's nice, because that's just going to turn into 4. All right, that's the first substitution, and then we're going to subtract the second substitution. So we get 9 on 2 times 3 on 2 squared. We probably should just square those, but since we're explaining things so well, let's just keep going. Minus 1 on 5, and again, let's put the 3 on 2 in. The 2 cancels with the 2 on the denominator, leaves us with 3. 3 plus 1 is 4, and that turned out really nicely as well. So we have 4 raised to the power of 5, and that's it. All right. So the substitution is done for the area under the curve. Okay, we do have to show our processes a little bit to get the marks. So we've done well so far. We've done the integration and substitution. Let's put the first brackets into our calculator. 9 on 2 times 15 on 2 squared minus 16, square root of 16 is 4. So it's 1 on 5 times 4 to the power of 5. And that's going to equal 48.325. All right, and we subtract the other brackets. So 9 on 2 is 4 on 5 times 1.5 squared minus the square root of 4 is 2. So we've got 2 to the 5 divided by 5 equals 3.725. All right, we subtract, and we're going to get 44.6. Oh, that's nice. 44.6, that's the area under the curve. We want to demonstrate we can find the area of the trapezium, and so we should write that, right? Area of a trapezium is h on 2 a plus b. All right, we worked out before that the length between them is 6 on 2, and a is the first y value. What were they again? It was 5.5. Plus the second y value was 3.5. Okay, and 5.5 plus 3.5 is 8, 9. 9, oh yeah, it was 27. Okay, 27. Okay, so the shaded area is 44.6 minus 27. And let's write that. (44.6) minus 27, and that equals 17.6.